Welcome to T3 Day 20 of Calculus. Today we're going to continue our discussion of differential equations. Remember, a differential equation is any equation with a rate of change in it. So this right here is an equation with a rate of change, dy dx. So it is a differential equation. Now mathematicians like to have different ways to word things, and this statement seems pretty long and complicated, but it's actually relatively straightforward. It says, find the general solution for the first order differential equation below. Now this is a first order differential equation because it's a first derivative. And when it says general solution, that means just find the indefinite integral. That's all it's asking you to do right here. So it's asking you to do this. And we know that that's going to be negative cosine of x, because the derivative of cosine is negative sine, but we want it to be positive sine. And then it's going to be plus 2x, because the antiderivative of 2x is 2x. And then there's a plus c. And it's a general solution because of the plus c. We would need more information to eliminate the c and make it a specific solution. So now we're going to find the particular solution of the initial value problem. So we're going to need to integrate this and then use this information right there to find c. So the first thing we're really doing is setting this up, and it's going to be the integral of 2 to the x plus 3x squared dx. And we want to do that indefinite integral. That is going to be 1 over ln of 2 times 2 to the x plus x cubed plus c. Now remember, this right here is the antiderivative of that, and the antiderivative of 3x squared is x cubed. You can test it by taking the derivative of this and seeing if it's that. It is. So we can simplify that a little bit and get 2 to the x over ln 2 plus x cubed plus c. So that's the general solution, but we want a specific one. We know that when you plug in 0, you should get out 5. So 2 to the 0 over ln 2 plus 0 cubed plus c should be 5. So that tells us that 5 is going to, sorry, I'll keep that on one side, 1 over ln 2, because 2 to the 0 is 1, plus c is equal to 5. So that tells us, I'll move this up here, that tells us that c is equal to 5 minus 1 over ln 2. So we just plug that in for c. So this is c, so it goes right there. So our final answer is going to be, so y will be 2 to the x over ln 2 plus x cubed plus our c value, which is 5 minus 1 over ln 2. That would be our final answer. We've got, that's not a general solution, that's a specific solution because we've eliminated the c value. We found the c value. So this one says, is y equals e to the 2t a solution to the second order differential equation? This. Well, second order just means it's a second derivative, and that's what second derivative, another way to write it right here. So there's a couple ways to test this. The best way to do it is to start here and take the derivative twice and see if it matches this equation. So if this is our first derivative, or sorry, our first degree function, so e to the 2t, so that if that is our function, what's the derivative going to be? Well, that's going to be e to the 2t times the derivative up here, which is just 2. So that's just 2e to the 2t. So now let's take the derivative again. So the derivative again is going to be that 2 is out there, but then you now have the derivative of this again, so it's e to the 2t times 2. So we know now that the second derivative is going to be, well, 2 times 2 is 4, 4e to the 2t. So that tells us that our second derivative is 4e to the 2t. So how do we check to see if it matches this right here to this equation right there? Well, let's take this and write it a little differently. That's written as this as well. You can write it as the second derivative written like that. That's the same way of writing it. So this and this, the same thing. And we're saying now that that, from our math, is equal to 4e to the 2t. So let's see what happens here. Well, what do we know? We know that y is equal to e to the 2t. Oh, you see it right there? So now we know that this, the second derivative of y with respect to t, is equal to 4 times y right there. This is the same as that, so then we just replaced it. So this is also right there. So is this statement true? Well, does 4y, let's plug it in there, plus 4y equal 0? No, it doesn't. It doesn't. This would have to be negative for it to work. So it is not a solution. It is not a solution. There'd have to be a negative in there. So in question 3, it says, suppose you're on a different planet and you drop a rock off a 100-foot cliff. So our initial position is 100. If the rock hits the ground after 5 seconds, so s of 5 is 0, the height after 5 seconds is 0, what is the acceleration due to gravity of that planet? The one other thing to notice here is that you drop the rock, so that means the initial velocity is 0. So what are we trying to find? What is the acceleration on this planet? Well, if we know the acceleration, we're trying to find it out, let's integrate. So we know the velocity is going to be a of t plus some constant. But the initial velocity is 0, so you know v of 0 is 0, which means that a times 0 plus c is 0, so c is 0. So we know our velocity is just a of t. So now let's integrate again to get the position function. So s of t is going to be a over 2 t squared plus a constant. But we know that when s of 0 is 100, so that means that when you plug in 0, 0 squared, you get 100. So since that's going to go to 0, c here is 100. So what do we know? S of t is a over 2 t squared plus 100. What do we haven't used yet? We haven't used s of 5 as 0. So we know that when you plug in 5, you get out 0. So a over 2 t squared plus 100 is equal to 0. So what does that mean? Well, we subtract 100, so a over 2. Oh, we plug in 5 for t, sorry. You plug in 5 right here for t. So that's 25 is equal to negative 100. So 25a is equal to negative 200. I multiplied both sides by 2 there. So a is going to be equal to negative 8. And what's that going to be? That's going to be in feet per second squared. So in this case, we started with acceleration, worked backwards, and then used all the information we had to get that right there.